This sixth lecture on Fourier series. Today we shall discuss what is known as half-range Fourier series. In half-range series, the function is specified in a range. Say f of x has been defined as defined in x less than c greater than 0. Then this is the original range. So original range is 0 to c. Whether it will be open or in closed interval, it will depend on the continuity of the function. Then one needs to extend the interval. Extended range is from minus c to plus c. That is, the function is defined in this range and one need to extend the function. We can extend the function, the extension in minus c to 0 can be done in two ways. By even extension of 0 to c range, or by odd extension of the original range. So if we extend the function in even mode, this is called the half range Fourier cosine expansion or series. This is known as half range Fourier sine series or sine expansion. Note that whenever we shall calculate the quantities, the delta will be 2c, not c. The calculation has to be performed with this. That is, in half range series, half of the range is supplied and one need to extend the other half, the lower half, and lower half can be expanded or extended in any way, even or odd extension of the original interval. Whatever may be the case, the function as estimated by the Fourier series will be same in this range. Only thing is that this part in this range minus c to 0, the function, the extended region of the function will be different as per the choice of series, sine series or cosine series. To make the concept clear, we consider an example that is function f of x is equal to x, and it is defined in the interval. So the original function is this. This is c, this is minus c, this is 0, this is f of x. And this is the x-axis. The original function is this. If we expand it in Fourier sine series, then this is the extension of the function in half range Fourier sine series. So this is c. So the extended interval is range is minus c to plus c, giving delta is equal to 2c. For half range Fourier sine series, only bn will be there, and the extension of the function has been shown in this figure. So this is 2 upon 2 pi 2c into 2, 0 to c, f of x sine of n pi x by c dx. You note that delta is equal to 2c, so these 2 on the numerator cancels with the 2 in the denominator. So this is becomes c, so this is 2, so this is 2 by c, 0 to c, x sine n pi x c dx. This is equal to 2 by c multiplied by c upon n pi. Then you will have x cos of n pi x c within limit 0 to c minus integration 0 to c cos of n pi x c dx. The lower limit it is, in the lower limit it is 0, and upper it is, and the upper limit it is minus 2 by n pi, this part on simplification, and this is c times cos of n pi, and this part when integrated gives sine, which is 0. So this is equal to this is the Fourier Sine expansion, the Bn value. And now if we expand this series in Fourier cosine series, half range Fourier cosine series of the same function. First we need to calculate a0. a0 is 2 upon 2c into 2, 0 to c f of x dx. This is 2 by c x dx from 0 to c. So this is simply c, and an is equal to 2 upon 2c into 2, 0 to c f of x cos of n pi x c dx. This is 2 by c, and when we integrate it we get c upon n pi, and within bracket this is x, you know, this is x. So we will have x sine of n pi x c within limit 0 to c minus integration sine of n pi x c dx within limits. This is 0. This part is 0 because sine of n pi is 0 and sine of 0 is 0. So we have this c cancels out, and this minus two upon n pi, and if we integrate it we will have minus c upon n pi cos of n pi x by c within limit 0 to c. So this sign is plus, so this is 2c upon n square pi square and this is cos of n pi minus cos of 0 is 1. For this is equal to minus 1 to the power n, and for odd This is the outcome. Now, when we expand this function in Fourier cosine series, that is, we are going for this extension, half range Fourier cosine series. One thing you see that the Fourier cosine series has the discontinuity at the ends, so it will give rise to Gibbs phenomena. But the Fourier cosine series is for this, the function is continuous, so there will be no Gibbs phenomena. Furthermore, for Fourier sine series, as the function has its discontinuity at the ends of the extended range, the Bn should have 1 by n dependence, and we finally see that Bn has 1 by n dependence. Whenever we extend this in half range Fourier cosine series, actually we assume the function to be mod x. So d of f dx is equal to plus 1 for x greater than equal to 0 and is equal to and is equal to minus 1 for x is equal to 0. So if the function derivative of the function has discontinuity, that is manifested by 1 by n square dependence of the expansion coefficient. Whatever be the expansion, this part will be estimated correctly with increasing number of n, where capital N is the capital N of the partial sum, nth capital nth partial sum. Another thing is that this series, since it has 1 by n dependence, will have a slower rate of convergence, but this series will have a faster rate of convergence. Say if we consider the first 4 partial sum of sine and cosine series, in that case for n is equal to 4, it will have 1 by 4, on the other hand it will have 1 by 16. So this term will have less contribution for n is equal to 4 compared to this. So this series will have a slower rate of convergence. This slow convergence. And this will have faster convergence. It will show Gibbs phenomena, no Gibbs phenomena. We consider one more example of this short. That is, we consider sine of x as this was the example number 8, and as the 9th example. Later, before going to this, let me show how the Fourier series will look like in these two cases. This is the Fourier sine series. This is half range Fourier sine series. If we allow this will be there will be the Gibbs phenomena. And for half range sine series, cosine series, half range cosine series, the estimation will be like this. Now we consider the next example, that is f of x is equal to sine x and is originally defined in the interval 0 to pi. We need to extend it to the minus pi to plus pi. So ninth example, f of x is equal to sine of x, x less than pi. So the extended range is minus pi to plus pi, so that delta is equal to 2 pi, and the argument 2n pi x by delta is simply nx. Now we first expand this series in half range Fourier cosine series. So the thing that I am going to do is that this is the function is defined in 0 to pi. This is the half range Fourier cosine expansion. So we first need to calculate A0. A0 is 2 upon 2 pi into 2, 0 to pi, f of x dx. This is equal to there will be minus 2 by pi cos of x between 0 to pi. So minus 2 by pi, cos of pi is minus 1, cos of 0 is 1, so this is 4 by pi. Now come to the an calculation. 2 upon 2 pi into 2 into 0 to pi, f of x cos of nx dx. This is 2 upon pi. Integration for this. This is sine of x cos of nx dx, including these two, we expand it as sine of n plus 1x minus sine of n minus 1x. So this is the cosine part, an part. And if we integrate this, we will get minus 1 upon pi. This minus sign comes from the integration of sine part. This is cos of n plus 1 x by n plus 1 minus cos of n minus 1 x by n minus 1 within limit 0 to pi. So this comes out to be minus 1 upon pi, this part, cos of n plus 1 pi minus cos of 0 is 1, and this is n plus 1. minus cos of n minus 1 pi minus 1 divided by n minus 1. So cos of n pi, now cos of n plus minus 1 pi is equal to cos of n pi, cos of pi minus plus sine of n pi, sine of pi. This part is 0 and this is minus 1, this is so this is minus 1 to the power n plus 1. On simplification, this becomes on simplification this becomes minus 4 upon pi n square minus 1 for n is equal to even and is 0 for n is equal to odd. So we get the Fourier expansion for that. If we use this, we will get for the Fourier half-range Fourier cosine expansion. So the summary is that for half-range Fourier series, A0 is for half-range Fourier series, A0 is 4 by pi and An is equal to minus 4 by pi n square minus 1 for n is equal to even and 0 for n is equal to odd. So we can expand the series. The half-range Fourier series, Fourier sine series is thus f of x half-range Fourier cosine series expansion of x is equal to sine x is equal to, this is 2 by pi because a0 by 2 minus 4 by pi summation over n square minus 1 cos of nx, n is equal to even, that is n will start from 2, 4 etc. 2, 4 etc. If we expand the series in half-range Fourier sine series, then only Bn will be there and we are estimating the function like this. So half-range Fourier sine expansion. It is expected that the function has been expanded, the sine function has expanded over a full range with the argument is integral times x. So the expansion should have only one term. Let me see what the calculation gives. Bn is equal to 2 by 2 pi into 2 into f of x sine of nx dx from 0 to pi, which is equal to 2 by pi sine of x sine of nx dx from 0 to pi. Including these two, we can write it as this is now we see what happens to sine of n plus minus 1 pi. So in the upper limit x becomes pi. This is sine of n pi cos of plus minus pi, then plus minus cos of n pi sine of plus minus pi, which is 0. So the result is 0 for n not equal to 1. So the result is 0 for n not equal to 1. And what happens to n is equal to 1? N is equal to 1, this term contributes, and we can write it sine of n minus 1x by this is pi. So after putting the limit, it is sine of n minus 1 pi by n minus 1 pi. In the limit n tends to 1, that is n minus 1 tends to 0, this tends to 1. So the result is 1 for n is equal to 1. So we see that only B1 survives, and this is what we expected from the observation. So this completes our discussion on half range Fourier series. In the next class we shall take up Parseval's equality.